Good morning, students. Welcome to the class on NMR spectroscopy. Now we will discuss about mechanism of absorption. So when we supply radio frequency energy to nucleus, nucleus will absorb energy. Then how it will absorb energy and what are the changes that will occur? Now we will discuss about that. Generally, the nuclear spin state, the nucleus will also precess like a electron. So to explain the precision of nucleus, we use a spinning top, which we used to play in our childhood. So the precision of nucleus is almost similar to spinning top. So it is always compared with spinning top. Now, what is a spinning top? Of course, we all of you have played with it in our childhood. So something like this, which we will use a thread, we will wound it around it, then we will throw it so that it will rotate. How it will rotate? It will rotate in this fashion, right? It will rotate like a cone like shape. So when we play this spinning top, it rotates on its own, and again it rotates it rotates according to the Earth's gravitational field. So this is the axis perpendicular to the Earth, but it will not rotate like along the perpendicular axis. It rotates with some inclination to the ground. So we can compare it with like Earth. Earth rotates on its own axis, at the same time it rotates around the sun. Similarly, this spinning top also, it rotates on its own axis, that means here. At the same time it also rotates like this in this circular fashion, so with some inclination. So when we look at from the top, we observe like a cone like precision. So this is spinning top, right? For a nucleus also, as we said, without magnetic field, it doesn't have the nuclear spin states are degenerate, but when we apply a magnetic field, what will happen? The spin states will be separated or quantized, and it tries to rotate. So in the presence of a magnetic field, what will happen? The nuclear spin, the nucleus tries to spin. When we apply a magnetic field, spinning nucleus in the magnetic field. When we apply a magnetic field, the nucleus tries to spin like a spinning top. So when we say it is spinning top, the axis should be like this, right? So it will be like this. And here also it will be like this. So in the presence of magnetic field, the nucleus starts spinning. The nucleus starts spinning. So the frequency of nuclear spin is represented by omega, which is called Larmor frequency. Larmor frequency. So the frequency at which nucleus spins, it is given by Larmor frequency. So the energy of the nuclear spin is given by H omega. Right. How the energy absorption takes place? What will happen under the magnetic field? The nucleus starts spinning with a Larmor frequency. Then what we will do, we will supply additional radio frequency energy, right? When we supply radio frequency energy of equal energy, that means when we supply h nu, that means frequency or radio frequency which is just equal to Larmor frequency, which is equal to Larmor frequency, then absorption of energy takes place. Absorption of energy takes place. Okay, when the frequency of spinning top is just equals to the frequency of radio RF waves, then energy absorption takes place. So what will happen when the energy absorption takes place? It undergoes inversion of spin. The nucleus undergoes spin inversion. So when the energy of radio frequency waves just matches with the energy of spinning nucleus, then energy absorption takes place. As a result, what will happen? The spin of the nucleus will be reversed. For example, if the spin of the nucleus is plus off, then when we pass radio frequency waves and if the energies are matching, then what will happen? Energy absorption takes place. Energy absorption takes place. Then it undergoes spin inversion. It undergoes spin inversion. Or in other words, how we can explain? For example, for a proton, say in the presence of magnetic field, it is alpha spin state and beta spin state, plus off and minus off. So for example, take one nucleus in the alpha spin state, then we supply same amount of energy, then what will happen? The energy will be absorbed by the nucleus. As a result, the nucleus from alpha spin state will now be excited to beta spin state. So in this case, what happened? Alpha spin state, they will undergo spin inversion. So as a result, nucleus will occupy beta spin state. So this is how energy absorption process occurs in an NMR technique. Right. So if you have some all proton nuclei, then all the proton nuclei will absorb energy. They will undergo a transition from lower energy to higher energy. Now we can calculate the energy difference between the lower energy and higher energy using Boltzmann distribution law. Boltzmann distribution law. How we can calculate? When we know the number of nucleus in the upper state and number of nucleus in the lower state, when we know the number of nucleons in the upper state and the number of nucleons in the lower state, then using Boltzmann distribution law, n upper by n lower is equal to e power minus delta E by kt. This is equal to e power minus h nu by kt. Here h is Planck's constant, whose value is given by 6.62 into 10 power minus 34 joule into second. K is Boltzmann constant, which is a ratio of R by N, real gas constant, to Avogadro number, which is again a constant whose value is 1.38 into 10 power minus 23 joule per Kelvin, and T is absolute temperature, Absolute temperature means we represent the temperature in Kelvin scale. Right. So when energy is absorbed by the nucleus, what will happen? The number of nucleons in the alpha spin state will take the energy. They will be shifted to beta spin state. So that is called spin inversion. For example, if you have the same number of nucleons in the alpha spin state and beta spin state, what is the result? When we pass energy which is equal to normal frequency, then what will happen? The number of nucleons in the alpha state will be excited to beta state. So this X will be excited to beta state. At the same time, the number of nucleons in the beta state will be coming to alpha state. So this X will be in the alpha state. Because these two the number in the alpha state and the beta state, the number of nucleons in the alpha state and beta state are exactly same. The same number of nucleons will be exciting from alpha state to beta state. At the same time, the same number of nucleons will be transferring from beta state to alpha state. So as a result, we don't see any nuclear transition, right? Because same number of nucleons are transiting from alpha to beta and beta to alpha. So this situation is called saturation. So when we don't see any signal in NMR, that situation is called saturation. Why it happens? When we apply a large excess energy than the normal frequency, then we observe a situation called saturation. When a saturation is reached, we don't see any signal in the instrument. Then generally the energy difference between these two spin states is very low, but still this energy difference is enough to have different nucleons in the alpha state and beta state. For example, for proton, when we apply 1.41 Tesla or what we can say 60 megahertz frequency, the alpha state will have 1,000,009 nucleons, whereas beta state will have 1,000,000 nucleons. So that means when we apply 60 megahertz, alpha state is having 9 nuclei excess. This excess nuclei is most important for us to get the NMR signal. So this excess nuclei are population excess here is 9. This 9 nuclei, this excess nuclei are very crucial for getting the NMR spectra. For example, if we want to calculate this N upper by N lower at 60 megahertz, then it is 1,000,000 by 1,000,009. It is approximately around 0.99991. So this excess nuclei is most important for us to get the NMR signal. So when energy absorbed by the nucleus, the 1,000,000 nucleons from alpha state will shift to beta state, 1,000,000 nucleons will shift from beta to alpha. Then we don't see any signal, right? But this excess population, 9 nucleons at 60 megahertz, it is most important because we will observe the signal because of the transition resulting from these 9 nuclei. So I'll give a brief relation between the frequency we use and the number of excess nuclei. When we use 60 megahertz, we will start with 20. We will have 3 nucleus excess. When we use 40 megahertz, it is 6 nuclei. When we use 60 megahertz, it is 9 nuclei. When we use 80 megahertz, it is 12 nuclei. So the difference is 333. So we can easily remember them. When we use 100 megahertz, it is 60 nuclei. This is the only exceptional. When we use 100 megahertz, it is the 16 nuclei. When we use 200 megahertz, 2 times this, 32 nuclei. When we use 300 megahertz, 3 times 2, 100, 16 into 3, it is 48. When we use 600 megahertz, 6 times 2, 100, it is 96, or double to 300. Or when we use 800 megahertz, it is 128 nuclei, that is excess nuclei. So with increase in frequency or with increase in applied magnetic field, what is happening? Excess nuclei are also increasing. So with this we can conclude that when we have high magnetic field or when we use high frequency radio frequency waves, we will have high very large excess nuclei which will give a very good signal. In other words, what we will say, it is a resolution of the spectrum will be very good. So that is why generally people always try to get the always try to use the NMR instrument with high frequency. Initially, people used to use 60 megahertz instrument, but the resolution is very low. It will have poor resolution. But nowadays, people are using 300 megahertz or 400 megahertz for normal organic compounds, and people are also using 800 megahertz for identifying polymers and biomolecules, proteins, nucleic acids. Okay, so yeah, nowadays most common instrument is 300 or 400 for biomolecules, proteins. 800 will be used.